Okay, 6.3 notes, exponential growth or decay. We're going to compare and contrast exponential growth or decay in the form y equals a times b to the x power. So your common ratio is when you have the multiple of the y values, whatever the y's are getting multiplied by each time, called the common ratio. So in this form of y equals a times b to the x power, notice this is an exponential function. The b value will give you your common ratio. The starting value, this is your y-intercept when x equals 0. That would be the a value in this form. So just like with a line when we had y equals mx plus b, this is the form for exponentials. So b is the common ratio, a is that starting value for your x equals 0, your y-intercept. So we're going to look at each table. It represents a point on an exponential curve. Identify the common ratio. So what are our y values getting multiplied by? So 3 times what makes 9? That'd be 3. 9 times what makes 27? 3. And then 27 times what makes 81? 3. So my common ratio, my b value, is 3. Over here, if I'm looking, what is this getting multiplied by each time? You should be getting 5 for your b value. And then for c, what am I multiplying by each time? In this case, I'm multiplying by 1/4. So I'm technically dividing by 4 as well, but when you're naming the exponential, you have to say in your b value what you're multiplying by. So you're taking 1/4 of something. All right, number 2 says to look at each table below and identify a, and then find b, which is the common ratio, and then write the exponential equation that represents the table of values. So this time I also have to find a. So notice the a value is your y-intercept where x equals 0. So my a value is 3. For my b value, I have to figure out what I'm multiplying by each time, which would be 2 each time. So putting the a and the b in, it'd be y equals an a value of 3 times 2 to the x power. All right, looking at this one, my y-intercept, my a value is 100. And then what is it getting multiplied by each time? That would be 1/2. So my equation plugging in a and b would be y equals 100 times 1/2 to the x power. So for exponential growth, it's when you have a b value greater than 1. So you're multiplying by something bigger than 1. So I'm going to make up some numbers here. So if I give you the numbers 2/9, 2/3, 2, 6, and 18, based on this whole table, the starting value, your y-intercept, is 2. Your common ratio, what is your y getting multiplied by each time? That would be 3. So putting these together for your equation, it'd be y equals 2 times 3 to the x power. And then if you were to graph this, you could graph 0, 2, 1, 6, and we know it's exponential, so it'll be curving up like this. So this is all exponential growth, multiplying by more than 1 with a b value more than 1. Your table's going up, and then your common ratio, notice more than 1, and then the curve of the graph is going up. Well, we can also have exponential decay. This is when you're multiplying by something between 0 and 1, but not including 0 or 1. So I'm going to make up some numbers for this. We're calling it 8, 4, 2, 1, and 1/2. So my starting value, my y-intercept is 0, 2. But this time, what is my y values getting multiplied by? They're getting multiplied by 1/2. So my equation is y equals 2 times 1/2 to the x power. And then when you graph this goes off the graph, but we have negative 1, 4, 0, 2, 1, 1. It's curving down like so. So we call this exponential decay. So it's multiplying between 0 and 1. So you're seeing fractions that are between 0 and 1 for your b value. And decay, it's going down, right? So determine if the situation is exponential growth or decay. So that means I have to figure out what my B value is. So I'm going to ignore the A value. I'm just going to look at the B. Since B is 4 and 4 is more than 1, this is growth. I need to figure out my B value here. So what am I multiplying by? 2. That's more than 1, so this is growth. All right, for C, ignoring the A value, looking at the B value, is that growth or is that decay? Okay, so that's less than 1, so this would be decay. This one's a little bit tricky. What is it getting multiplied by? Nothing. It's actually subtracting by 100. This means this is not exponential at all. It's a linear pattern. So when you're adding or subtracting, it's linear. When you're multiplying, it's exponential. All right, looking at this one, my A value you ignore. I'm just looking at the B value. 3 over 2, that's 1.5. So that's more than 1, so it's growth. And then over here, you're multiplying by 1/10, and that's less than 1, so this would be considered decay. Okay, so maybe put a little star next to this one. Students struggle here. So for your percent increase, it ends up when you're increasing by a percent or decreasing by a percent, it's exponential in pattern. So percent increase is when you're increasing by a percent over time. If you think of it as if you're making a certain amount of money and I give you 100% of what you're making, I didn't give you a pay raise. So you have to go above 100% of what you're making in order to give you a raise. So you're going to add whatever your pay raise is to 100%. So if I decide to give you an 8% increase in pay, you don't want me to pay you 8% of what you're making. You want me to make you 100% of what already plus another 8%. So that's why you're going to add them to get 108%. But your B value is the decimal form. So notice this is the decimal. It's going to move to the left too. So my B value is 1.08. All right, so percent decrease is when you're decreasing by a percent over time. If you all of a sudden aren't working very well and you want me to, and I want to pay you less, you again don't want me to pay you 8% of what you're making. That would really not be fair. But if I was to deduct this from what you're making, it would make sense to subtract from 100% of what you're making. So let's say a company is having a 5.2% decrease in profits. So you do 100% minus the 5.2% and get 94.8%. And then we need the decimal, so move the decimal over twice. So it's 0.948 as your percent B value. All right, so it says for each function below, identify the percent rate of change and classify each as a growth or decay model. So notice this has a B value of 1.04. So that means the percent increase is a 4% increase, as the decimal would move over twice, 4%. And that's more than 1, so this would be growth. This one, if I move over twice, that's 85%. How is that a change from 100%? Well, it's a 15% change, and that's decay, because notice 85% would be less than 100%. Then 0.97, what would be the percent change? And would it be growth or decay? Okay, so you should be getting a 3% change from 100%, and that would be decay because it's less than 100%. And then what about D? What's the percent change, and is it growth or decay? Okay, the change from 100% is just a 1% change, and it's growth because it's more than 100%. All right, identify the common ratio for each of the following exponential situations. So Starbucks is growing 3% every year. So if it's growing by 3%, you would add that to 100%. So it's 103%. That B value as a decimal is 1.03. Bacteria double every 30 minutes. So this is not a percent. Don't try to make it a percent. Doubling means I'm multiplying by 2. Don't make it more complicated than it needs to be. A company is closing half of its stores every year. So you have a B value of 1/2. Or if you want to do percents, that'd be 50%, so 0.5. It's the same thing. A car depreciates, goes down in value, 8% each year. So you don't want it to be worth 8% what it's worth. You subtract it from 100. That'd be 92%. And as a decimal, it's 0.92. Okay, number 6. I'm going to go ahead and skip this just for the sake of distance learning. Here we go. Number 7. I'm going to skip around a little bit here. It says the amount of bacteria started with 1,000 and then grows 3.5% each month. So in this case, the initial amount of bacteria was 1,000, so that's my A value. And then my common ratio, what am I multiplying by? It's growing by 3.5%. So I'm going to add that to 100% and get 1.035. Then it says to find the number of bacteria after 1 month. I'm going to skip that. I'm going to go to C. We're going to write an exponential model to represent the growth of bacteria after X months. So it's Y equals my A value times my B value to the X power. So going back to B, if I'm trying to find the number of bacteria after 1 month, I'm going to put in a 1 for X. And that would be typing into my calculator 1,035. Now jumping to D, it says to use your equation to predict the number of bacteria after 2 years. Well, remember X is months, not years. So how many months was 2 years? That means I'm plugging in 24 for X. So typing that into a calculator, I get 2,283.33. All right, so most cars don't appreciate in value. Instead, they depreciate. The current rate of depreciation for most cars is 9%. This is true. The most popular vehicle is the Ford F-150, and it costs $25,000. This is a couple years old now, so I'm sure that's a little bit higher. But write an exponential model for the price of the truck. You're up. Okay, so the truck is starting with $25,000, so that's your A value. And then it's depreciating 9%, so it's 100% minus 9%, so it's 0.91, and that's to the X power. We're going to make a table and graph the data. So you can use your calculator to fill in these tables, or you could just change the X value on your calculator. It's up to you. I'm just going to quickly give you these values. So if you plug in 0 for X, you're going to get $25,000. After 5 years, if you plug in a 5, you're going to get 15,600.80. Plugging in 10, you're going to get 9,735.40. After 15 years, it's 6,075.20. After 20 years, it's 3,791.12. After 25 years, it's 2,365.78. 30 years is 1,476.32. 35 years is $921.27. 40 years is 574.90. 45 years is 358.76. And after 50 years is worth $223.88. So quite a bit difference over 50 years. We're going to graph this. So this is going to be the number of years old on your truck and then the value of your truck. So counting by 5 years, the value of the truck has to get to 25,000. So we could count by 2,000. So when we graph this at year 0, we knew it was 25,000. And then it's going down and down and down and down and down like so. Notice where the biggest drop in price went. So notice the first 5 years is where you lose the most money on the vehicle. This is why people tell you, if possible, don't buy brand new, because that's where you're losing your most money. If you buy a 5-year-old vehicle, notice you're still losing money, but not nearly as bad as the first 5 years. And then notice if you buy a 10-year-old vehicle, it doesn't drop that much in price. So what's the price of the truck 100 years from now, plugging in 100 for X? $2. Wow. And will it ever have no value? No, you could sell the screws or something, right? You could get some scrap from it.